All right, everyone. So we're at the top of the hour. We're glad you could join us today. So we're here to talk about training, code performance, and scaling on the different Exceed resources. My name is Ken Hackworth, and I'm here with Dr. Lars Kostricki from the University of Texas, the TAC Center. My role is the allocations manager for the Exceed allocations process. So some of you may have seen me in other places. So we're going to cover code performance and scaling. It's an integral part of research requests for Exceed allocations. And it's an area that we felt was needed to help potential PIs or existing PIs to improve on this for their proposals. So we are going to begin. A couple housekeeping notes before we start. We're recording this session. It may be used and displayed in our educational sites, as well as linked to from the allocation site. Also, we ask that you stay muted. If you have questions, we will use the chat box. It'd be perfect. We may turn that off and allow some interaction as we get towards the end. But until then, we'll go with that and then we'll answer your questions and all. So the first part that we would like to talk about is the code of conduct. Since this is an Exceed function, you all should have seen this, or at least you had clicked on the box when you registered for the class. But we have a code of conduct. We'd like to be nice and fair and have a great calm debate today. And as you see, I am one of the event organizers as well as one of the ombudsmen for the code of conduct. So if you have any concerns or questions, whatnot, there was a link there at the bottom where if you needed to, you could let us know that you have some concerns. The next statement is our terminology statement. So we've found recently, but we've noticed this, that there's some terminology that is just not appropriate or may be offensive to some or all. So we are working through this. Some of the documentation, we have cleaned this up. If you have any concerns, please let us know at terminology@exceed.org. Some of them we have no control over, but we will do our best to control what we can. So the extreme science and engineering discovery environment exceed our mission to substantially enhance the productivity of a growing community of scholars, researchers, and engineers through access to advanced digital services that support open research and coordinate and add significant value to the leading cyber infrastructure resources funded by the NSF and other agencies. So this is our mission. And those digital services, they come in compute and storage and ECSS and SGCI services and all. But again, we are here to, next slide, Lars. Yeah, perfect. So we want to have, provide users with this seamless integration to these resources or services. So we're here to work with you all with the code of performance and scaling and through allocations and the ECSS group to make this process seamless and hopefully easy for you all. So the portfolio that we have, so for these research grants and all, we have the HPC systems, the Comet machine, the Expanse machine at San Diego, and the Bridges machine at Pittsburgh, the Jetstream machine at Indiana, the TAC Stampede 2 system, and all the high throughput or HCC systems we allocate. OSG, Open Science Grid, and some other systems. Then we have the GPU and AI systems across multiple sites, San Diego and Pittsburgh, have these systems with others coming, visualization and data analysis systems, large memory systems, data storage, cloud systems. And then, as we note here, Exceed staff, this is ECSS, Extended Collaborative Support Services, and SGCI, Science Gateway Community Initiative. These are people, some of the best resources that we do have in Exceed. And let me note here, these digital services, the landscape is changing quickly here. There's 2 new machines coming into production this fall, Expanse at San Diego and Bridges 2 at Pittsburgh. with other machines coming, some category 2 machines coming, and as well as some new machines coming for 2021. So the landscape is changing. A lot of good resources, a lot of new resources coming. So this is why we want to make sure that you have the opportunity to get on these machines and do some testing. So so we like to talk about startup allocations, why you would want to request a startup allocation and how to get one. We, on the XSEDE allocations page, it's a very simple thing, as long as you're eligible, and that means you have you're a faculty member, a postdoc, a researcher from an institution. As a graduate student, most likely you wouldn't be eligible. You could work through your advisor to get on and get access to these systems. Either you could be a co-PI or allocations manager, or if you, as a graduate student, you may have an NSF fellowship that makes you eligible for a startup, to be a PI on a startup. But there's no deadlines. These can be requested at any time. We review these in less than 2 weeks. I think our average is something like 7-8 days. We get to turn around for you. Multiple resources can be requested. It's not just an individual. You can request all of the different XSEDE resources. The purpose, again, and that's leading up to our why we're here today, is these small computational activities, application development, evaluation, and experimentation on the different systems, and then benchmarking for code performance and scaling here today. These all lead or are mostly a precursor to research allocation. So in a research allocation, after you've gone through the startup phase and you've done this testing and all, these are where there is a mandatory document called the Code Performance and Scaling document. And that's what we're going to talk about today. These proposals or research allocations are unlimited in size. They are reviewed quarterly by an XRAC panel of peer reviewers. One award per PI, not multiple PIs, not multiple grants by one PI. We see a lot of these here. It's a highly competitive process. We see greater than 200 research proposals per quarter. The most recent meeting we had in late August, there were 227 proposals. But proposal quality matters here, and that's what we talk about. There's also another webinar that I do about writing and submitting these proposals, and then this webinar along with Dr. Lars Kostriki about the very important part of the code performance and scaling. And you see here that we award greater than 80% of the research requests that come in, but a large number are declined because of they just haven't done the homework and the legwork of doing testing, and they have poor code performance and scaling, or they're not picking the right job sizes and core counts or node counts and all. So this is important to follow along with what Lars is going to tell us today, and the best way to predict or pick or choose your efficiency of these resources. And I will hand the next slide over, starting with Dr. Lars Kostriki. Thank you, Lars.
Yeah, hi everybody. My name is Lars. I'm a longtime member at the Texas Advanced Computing Center in the High Performance Computing Group, and I have been doing reviews for over 10 years now. And so I try to base my hands-on advice on things that I like to see in a proposal and the way I like it presented, and it's a kind of consensus how other people like to have that as well, other reviewers. And you know, a review is a highly subjective process for an individual review, and the fairness comes in because there are multiple reviewers, and then there's another process on top of it. You have to deal with reviewers. They have certain expectations, and you have to provide data so that you convince the reviewers that your computational plan is sound. And that is what I would call a well-justified computational plan. And that should be the backbone of your successful XSEDE proposal. The science is, of course, important in your proposal, but the reviewer will focus on the computational plan. That is particularly true for funded projects. where the science is not reviewed per se. If you don't have external funding, then the reviewer may even review the science. And nevertheless, the reviewer will always make sure that the computations that you are suggesting is matching the scientific questions that you are posing. So there's always a science part, and science also plays a role later on in estimating your total number of SUs. Another thing that is paramount is you want to demonstrate competent use of these resources. They're expensive. There's a competition. It's a fierce competition, and so you have to demonstrate a competent use. And otherwise, if you leave doubts, there will be consequences. And we will delve into components of what a well-justified computational plan is in a minute. My hands-on advice, I try to sprinkle in a lot of hands-on advice here, is that your proposal is not your NSF proposal and then you add 2 sentences and say, yeah, I need that much, that number of hours or that size of a resource. That will not work. I'd like to proceed in the following way. If you have questions, already put them in the chat room, and most of the questions I can probably already answer right along. And then at the end, there's ample of time to ask more detailed questions. I also want to highlight or point out that, of course, all my advice is kind of applicable for 80% or 90% of these cases, and you have to always read a little bit between the lines of where it applies to your, or how it applies to your specific needs. It can explain that you can do a startup a proposal. There is really not that much to do. You get a generous amount of time, and you will use that time ideally to provide or to produce all the data that you will need to create a successful full proposal. And so you go from a startup to a full proposal, and there's a lot of common sense advice. Obviously, requests from new groups are under more scrutiny than proposals from well-established groups. If you're well-established, you have a better chance of winning really large awards. Because it is always expected that PIs establish some kind of a track record. Yeah, the competition, of course, for larger proposals, there is more competition. For smaller proposals, there's less competition. So larger proposals are more scrutinized than smaller ones. The rest I don't understand, as in always are given for less than asked. Maybe Scott, you can clarify later so I can understand the question better. So my advice is always that you compare your request size to the availability of the resource. And while we are not publishing these numbers, you can easily find out how many nodes there are in a resource and how many SUs are how many nodes there are, you know how many, what the availability is of all the SUs, and so you can gauge your request against that. And I guess it is kind of common sense. If you would ask for 10% of what a resource provides, that would be outrageously large with 200 proposals that we get every quarter. So you have to limit yourself to reasonable fraction of the target system, less scrutiny for smaller requests, and you focus on what you really need. So there are, of course, multiple resources that do in principle the same or provide the same capability, and not just for convenience, ask for all of them because, you know, the system could be down or something. That may inconvenience you. That is not what we like to have. You have to focus on a system, and don't add multiple systems that basically provide the same capability. Can I get repeated startup allocation? Yeah, I think that is for Ken. That is of course possible. So hands-on advice, use common sense when preparing your proposal, pick a reasonable size. Also, the second point, I think that's the most important one. You will compete with a lot of other groups. Those are experienced groups. You will compete with very well-written proposals. And if you write a good proposal, you will be rewarded for that. So it's really something that where you get a reward for putting in more work and writing a better proposal. And if you're overly ambitious, you will not fare well, and that is particularly true for new PIs. So what are the details of such a proposal? You are competing, you want to know what do you have to do there. So on the left, I have some basic outline. So there's a description of the science, there's some detailing of the specific scientific questions that you want to address. You describe the software. If it is not well-known software, you describe how it is parallelized, all these kind of things. And then 4 and 5, those are the most important parts. You write a computational plan, and we go into some details about that. And you estimate the total number of service units that you want to request. And that estimate and the computational plan is based on supporting data. That is bullet point number 6. And that supporting data, that is scaling information, and that is something where the reviewers can judge the computational efficiency of your software or of how you want to set up in the computational plan. And so a lot of effort or a focus in this talk will be on how to create the supporting data, and then how to estimate the number of service units, and then put that all into a computational plan. So on the right, I have some details. A proposal are in some form or shape, all proposals are all the same, but your proposal is not your NSF proposal. It is with a specific focus on the computational plan. Keep in mind when you write that the reviewers are of course knowledgeable in the general area of what the proposal, what you want to do, but they are not necessarily domain experts. So a broader approach explaining what you want to do is always appreciated by reviewers. What you have to do is you connect the scientific questions to the computations that you want to propose. You demonstrate or explain how these computations will advance you towards answering these questions. You have to detail a little bit what equations or algorithms are applied. Of course, it depends. That is different from a field of science, or if it is a homegrown code, or if it is a community code that is well known. So if you work in molecular dynamics, you certainly don't have to explain what the algorithm be underneath your molecular dynamics code, your community code is. But you have to do some kind of description so that the reviewer can follow what you want to do. It's always good if you did something special to increase the performance, to highlight that as well. I will go into more details later. That bullet point number 3 is has the focus on you want to assure the reviewers that you know how to run the code, that you know how to run the code on the target system, that you know what you are doing. Now, when you present your computational plan, it should have details on the number of calculations that you want to do, what the runtimes are, what the node counts are, and how this relates to your scaling data. So there should be sentences like, you can see from the scaling data, it takes this long to calculate 5 time steps of my problem, and then you extrapolate to the number of time steps that you need. Details, yeah, I go into all this in more detail. And there should be basic math that allows the reviewers to verify the total SU estimate. So we go into that as well. And the scaling, that's bullet point number 6, that is basically your proof to the reviewer that you can efficiently use the resource, and you will use that to justify the size of for individual calculations, and you will demonstrate scaling efficiency, estimate total runtime, and reviewers will appreciate all efforts that you in that area in your document. So the computational plan takes center stage, your computational plan, and your resource justification is not just presenting a number. Reviewers want to be assured what you are doing, and if there are doubts, then they will suggest a cut, or if they are unsatisfied, they will reject your proposal, and you will have to resubmit a better proposal 3 months later, or at a later point. 3 months would be the earliest. Now, it is, of course, difficult to judge the efficiency of an application if you want to get a complete picture. So here we have to take some shortcuts. So the review panel will be using scaling efficiency as a proxy for the efficiency of your application. What that means, we see in a minute. Reviewers like to see scaling on the target system or on a similar XSEDEYS system, not on the old cluster that you have at your university or some completely different architecture you have somewhere else, because if you use a different architecture, then in the end, it will be much more difficult to estimate the actual number of SUs that you will need. And you will present scaling data for a typical case. You present timings for a few time steps or for a smaller sample. And that depends all what kind of code you are running or what kind of problem you want to solve. There you have to read a little bit between the lines and pick what is right for your situation. If you have more complex situations like AMR, then you have to get by using a more simplified setup and discuss the implications of your AMR levels, for example. The documentation or the scaling should cover the number of nodes that you target for production, or you apply a well-justified extrapolation. Again, you base that on the scaling plots, and once we discuss in a minute how those would look like, I think it becomes clear how that would work. Always target node counts for production runs where the scaling is good. I think that's a no-brainer. That is, of course, what you should do, but there's often a misconception of what does it mean where the scaling is good. So many proposals are rejected because the PI does not fully understand that that he or she has already moved into an area where the scaling is actually not good anymore. And you will have to balance, of course, wall clock time versus scaling and parallel efficiency. And I will have some remarks on that later. Oh, there are more. No, there are no more questions. I think I'm all good. Okay, so we have to talk about speed up and parallel efficiency, and it usually comes in 2 flavors, and those flavors are called strong scaling and weak scaling. And for both, I want to go through some example to show you how you would use the data and how you would present it. So in strong scaling, the workload is kept constant. It is a fixed workload, and now you throw more and more resources at it. And ideally, the execution time decreases with the number or the size of the resource. So if it takes on 1 core an hour, you hope it takes half an hour on 2 cores and 15 minutes on 4 cores. And that is how you should present it. So whatever you use as baseline, it could be either cores or it could be nodes, depends on your problem. The speed up is, of course, the ratio between these execution times on 1 core or node, on 2 cores or nodes, and so on and so on. And there it strongly recommended that you use something like T1 over Tn, because in this setup, the ideal strong scaling is a linear function and hence easy to assess and ready to assess for parallel efficiency. If you do the inverse Tn over T1, then your ideal strong scaling is a curve that is 1 over x, and that is much, much harder to judge. In that same case, usually linear axes are chosen. Reviewers are, of course, aware that on a single node, if you do strong scaling experiments in particular, that the performance will flatten because most likely you will run out of memory bandwidth. But if you present an experiment like that, there should be, I would recommend to at least explain it a little bit, or at least have a note there. Strong scaling experiments are often conducted for smaller calculations on a single node. So for smaller calculations, you see that much more often. On my next slide, I have my little example. So on the right here, x-axis is course or node, and y-axis is the speed up. And if you do it right, the ideal scaling is this linear curve or line. And your measured speed up is, of course, something that is not ideal. It is very good at the beginning, and then at some point it reaches a maximum, and then it tips over. I guess if anybody would agree, you would not use anything beyond the maximum. But I want to point out that you also should not pick where you achieve maximum speed, because you will have lower parallel efficiency. And if you go to a smaller core count then, or node count, then you could do the same calculations without while using or consuming less service units. And the service units that you are not using will be used by somebody else. So you have to be in the green or in this orange scenario. And to preserve the linear relationship of your ideal scaling, the axis should be either both linear or it should be log-log, but it should not be log-lin. If you do the inverse, then that is my example on the right-hand side here. So now your ideal scaling is 1 over x, this blue curve. And now the reviewer has to judge this other curve, the orange one. And there it is often very difficult to understand, is the scaling efficiency still good or is it not so good? And I guess most of you have reviewed proposals yourself. The moment the reviewer has a doubt that there's something going on that is not that easy to understand, that can always lead to a harsher review or a harsher result than need be. If a reviewer becomes suspicious, or when the reviewers come together, I often find that one of the reviewers brings something up and then all the other reviewers have a closer look and agree, yeah, that doesn't look well. And those are usually proposals that do not fare well. The other way to approach scaling is through weak scaling. In weak scaling, the workload is proportional to the amount of work. And so as more and more resources are applied, you increase the amount of work. Now, in a perfect situation, now your execution time would be constant, because every core or every node in your setup would always do the same amount of work. And in that case, we usually talk about the parallel efficiency, and that is the ratio of execution times on one node, on 2 nodes, on 4 nodes, and so on. Again, for keeping in mind that the amount of work is proportional to the number of nodes. In that case, you would use T1 over Tn. So if Tn, your scaling, if a parallel efficiency will not be 100%, but below 100%, and if you if you plot T1 over Tn, then or calculate that, then you have numbers that are ideally 1. And once you leave the ideal setup, then they become, then they go below 1. I think that is very easy to understand in the weak scaling scenario. These experiments are often for larger calculations on multiple nodes, hundreds, thousands of nodes even. Yeah, one word of advice: in some fields, it's very common to use the progress within the calculation as the measurement rather than the execution time. Time steps per hour is a good example, or if you do molecular dynamics, femtoseconds per wall clock second. I think that is perfectly fine, but you should keep in mind that not all the reviewers are domain experts. So it helps if you add a sentence that explains the units a little bit. And sometimes it even helps if you add this cheesy lower numbers are better or higher numbers are better. So just to help the reviewer to get the review done quickly and efficiently. And yeah, we all know if we are getting hung up in reviewing a proposal for too long, none of us likes that. The moment the reviewers feels confused, my approach is always, if I get confused, I think that the proposal is not well written, and then I start having doubts if that is all fine and dandy, and then I start worrying if cuts are should be recommended or if the proposal should be rejected. So here is my diagram for weak scaling. I have the nodes at the x-axis, and I have the parallel efficiency as the y-axis. And so for the parallel efficiency, it goes from 0 to 1. And now for the x-axis, it could be linear or log scale, depending on how wide of a range of you need to cover. There's good scaling where you are at a good parallel efficiency, and then your parallel efficiency will turn over at some point. That is where it's still reasonable, and then when it tanks, that is bad scaling. Now, I think I should upgrade this plot at some point, because there are, of course, cases where the parallel efficiency is never really 1, but it is, let's say, 0.6, but at least it stays flat at 0.6, and then you can still use that up to the point where then you have kind of this, the point where your curve bends. Yeah, another hint is that for large calculations, of course, you very often cannot boil down a calculation onto one node, or maybe not, or even more extreme, onto a single core, because you will run out of memory. In that case, you will use the smallest number of nodes that you can use for this experiment as your baseline, and then you expand from there. Reviewers understand that. You just have to explain it a little bit if it is not completely transparent right away. So use common sense when picking a target scale. For large calculation with a high SU consumption, absolutely do not pick large and quick turnaround and quick completion at the expense of efficiency, because you will be wasting so many SUs that somebody else, some other project, could put to good use. In these scaling plots, you demonstrate that you will use the resources efficiently by picking a scale where your performance is good. The review panel is not overly concerned with wall clock time. Your award period is typical for a year, and you are expected to run through that whole year. So you cannot make that argument. You want to run everything in the first month, and you are willing to sacrifice 50% of efficiency for that. The review panel has no, it's not sympathetic to that idea. Of course, everything is not really perfect in real life, so you always have to find a good compromise. And we all have written proposals. You present your data in a favorable yet transparent way. So you do it in a favorable way without raising suspicion by for the reviewers, so that they are not that they don't have the feeling that you are hiding something, or that not everything is as good as it should. But you should certainly write or present your data in the most favorable form. So you balance efficiency and runtime or wall clock time. If you're in doubt, you have to be on the efficient side. That is my advice. Allocation is typically for a year. You cannot argue you want to do everything in a much shorter time frame, because that is much more convenient for you, because that would be an argument that would be true for basically everybody. You reduce wall clock time by advancing multiple calculations simultaneously. So the reviewer will, of course, look if you can go through, consume all your SUs within the year's limit. If you can do multiple calculations, the reviewer will assume that you do them concurrently. And you have to, it helps if you explain that. If you have one very simple, long calculation, if you would need to run 24/7 on a system for 365 days to get this done, then that is certainly not feasible. You have to keep in mind that your jobs is in the queue, and that there's a wait time for that, and that there's always some overhead. So whenever I read a proposal where I come to the conclusion that the code has to run for more than a quarter or for more than a third of that given year, then I start to become suspicious that the project is just not feasible the way it is set up in the proposal. For time-critical projects, of course, the rules are a little bit more relaxed. So you're doing weather forecast for real weather events like tornado forecasts, stuff like that. Of course, everybody understands that your forecast cannot be a hindcast to save some SUs. Nevertheless, wasting 50% of your SUs at some point, that becomes also difficult to argue. So if you push too far into inefficient territory, you will be told to optimize your application, or to revise your strategy, and you will receive you may receive a severely reduced allocation, where the reviewer will propose to give you some time so you can optimize your code, and then you come back in a year later, and you then get your science done. When you do small but numerous calculations, like you have 1 million of jobs that run on single cores, you have to investigate how you bundle those on a single node. On many resources in XSEDEYS, the nodes are not shared. So if a node has 16 cores, you would have to bundle 16 of these calculations onto a single node. It is up to you to investigate that and to present a strategy in your proposal. Certainly, XSEDEYS staff can help with that, but it is really a burden on you. You have to also investigate and present the most efficient setup. So is it the best to run 16 individual calculations serial on 16 cores, or should I do 4 calculations and each calculation uses 4 cores, something like that. So that is also something to investigate if you're not after large calculations that scale out, but you're doing basically high throughput computing. Now, when you estimate the number of SUs, you present some simple math to estimate the total the total request. You use the timing from your scaling experiments and you extrapolate towards the total number of time steps or the size of the problem, whatever is in line with your calculations at hand. You present hands-on advice, you present details for all planned experiments. You allow the reviewer to easily follow your estimate, so to easily follow the basic math. You give reviewers the reassurance that your estimate is not bloated. And I always find it very helpful if there's a table that summarizes all these individual experiments. For parameter study, you have to highlight, or I would recommend to highlight, that you selected a reasonable small number of parameter combinations. So your approach is not, I try all parameter combinations and then I throw away all the unreasonable results that I don't need. Reviewers want to be assured that in parameter studies that you have pruned your sample size. Potentially discuss how the initial calculations will or may inform the selection that you make later on. That is also, if you can do that, that is something that reviewers like to read about or that they appreciate. There's always the issue of storage. If you don't justify your storage, you will just get the default amount. Here's my example of what simple math would look like in such a little table. We start with the simple math. You want to calculate how many SUs you want to request. That is the number you want to derive. That number is easy to derive. First of all, you have the number of nodes or cores that you want to use in a given experiment. That is information you get from your scaling data. From your scaling data, you also know what is the total runtime to accomplish all the time steps that you need, or to cover the computational area when you scale up to larger and larger computations. And of course, you know the number of simulations. And of course, if you have multiple types of simulations, you have to have kind of individual calculations like that, or present basic math for all of them. So from the scaling plots and your scaling data, you use that to justify why you have picked this certain number of nodes or cores, the size of the resource you want to use. And from the scaling and performance data, you use the performance data to map the simulation time to the total runtime. And the third piece you need for this simple math is that from the sciencey bits in your proposal, you argue why you need a certain resolution or why you need a certain simulation time. That comes directly from your proposal. So in molecular dynamics, why you need to run that many not milliseconds, that many microseconds, and so on and so on. Or if you work on PDEs, why you need the resolution that you are suggesting. And so in a table, this could be a useful setup here for you. You describe kind of shortly, you have an entry of what experiment that is, what method is being applied, what resolution, what simulation time, number of nodes, total runtime, number of simulations. Your situation will vary. You will know which columns apply to your problem and which columns don't. And then basically you present the SU amount for all your experiments. And me as a reviewer, what I do is I read basically the proposal backwards. I start with the computational plan, and if the computational plan has a table, then I first get an overview of what is in the table and what are the largest entries there, and then I will of course focus on those. Nobody will get hung up on 600 SUs if if you're in the review process, it turns out that the 240,000 SUs were justified. And so you present easy to digest information to the reviewer. And if this is a made up example, so everything looks super neat, but now the reviewer can immediately see, okay, simulation time, number of nodes, total runtime, and so on. And if the reviewer has doubts, why is the simulation time so long, then the reviewer can go back and read individual parts of your proposal with more scrutiny. Make it easy for the reviewers. That always pays off. Oh, there was one. Yes. Provide relevant information for all methods and experiments. Within reason. If there are, of course, very small experiments, then you don't have to go into all the details. There's, of course, the topic of community codes and well-known codes. For those, you still have to provide scaling information because you want to demonstrate that you will use the appropriate number of nodes where your parallel efficiency is still good, and it does not help if you just say, everybody knows the code scales and I want to use 100 nodes. Scaling should be specific for your setup. In community codes, you can cover often a wide range of experiments and sizes. So reviewers want to see something specific to your proposed calculations. The scaling again should be on the target machine or a machine with a very similar architecture. And then if everything comes all together, you can present an accurate estimate of the SUs, and the reviewer will then agree with that. Present scaling for a typical case, use your results, and very, very important, do not refer to external documents where scaling for these common community codes are documented. The reviewer doesn't want to read more documents, click at something, read a paper or a chapter in a paper. It has to be in this one document or in this small number of documents, your proposal, your scaling information, and so on. It has to be all in there. Reviewers will not read other documents. That is just not what they do. And put yourself, remember when you did your last review, it's already a long proposal, and now the PI suggests you read another paper. That usually doesn't go over well. The reviewers want to read about your experiences on a specific system. They want to be assured that you know how to run this community code on the target system. There are some additional considerations, and then we are already at the end. So your request is, of course, not only about compute SUs. So you have to talk a little bit about storage, either long-term on tape or medium-term on disk. So if you want to get more than the default, you have to say a word about that. The justification is not that elaborate compared to your SU resource justification. Reviewers have a feeling of how much storage would be a reasonable amount for the kind of calculations that you want to do. But again, the more storage you ask for, the more elaborate should your justification be. Also, if you have special queuing demands, you should mention that as well. Of course, that is only for very well justified requests, usually when the real world is being tackled, weather forecasts, things like that. It is not okay to request special queuing priorities just because you want to get your calculations done earlier. For the obvious reason, everybody would then do that. If you anticipate problems running the code on the cluster, it always pays off to be open about it. Resource providers are happy to work with you before you cause problems on the system. And this is usually not taken or held against you in the review process, unless the reviewer is convinced that this problem comes from some problem with your code or some problem with your setup. But usually you will not be penalized by adding those special requirements to the proposal. Discuss bottlenecks. Usually it is I/O. That is usually a problem. Sometimes it is file transfer if you have your data on a different machine and you need to transfer that. But I mean, nowadays the internet too is so fast that usually the transfer is not a problem. And my hands-on advice is, yeah, that is, I think, very important. Anything you have done with the code to enhance performance, you should always write about it and brag about it. Have you done any of these? Have you made efforts to understand your code performance? Did you do profiling? Did you do code optimization? Did you do scaling optimization? Did you do optimizations to optimize I/O or improve I/O performance? Reviewers like to read about it because it gives them the impression, rightfully so, that you know what is going on in the code, that you have looked for problems or that you have looked for things that can be improved. So they always like to read about that, write about your efforts, it will pay off. And now I'm already on my last slide. Design your proposal around the computational plan, demonstrate efficient use through the scaling. Keep in mind that this is a proxy and the reviewers, of course, know it's a proxy. The whole setup is, the whole process is set up around this being a proxy. Have some basic math to estimate the total SU request size. Be reasonable with the total size. If you ask for a lot, compare it to a rough estimate of how many SUs will be made available every year or every quarter. And be prepared that you have to ramp up over time. There is tough competition, and if you accept that, and if you're willing to write or put more effort to write a better proposal, that will go a long way. And I think then I'm done, and we have ample of time to answer all your questions. And I guess Ken will unmute and tell me if what questions I missed or something I can clarify.
Well, Jay and I have been answering many questions. There's one that I'd like to answer. I'll do it verbally. Dong Chen, you ask, thanks for a nice talk, very clear about all the key points. Thank you for that. Lars did a great job. One question for the renewal process with the new project added. Should we submit exact same main document as last year and add the new project in the progress report, or should we submit a new main document? Yeah, you should. You definitely should submit a revised main document. I mean, some projects are the same year after year, but most likely they've changed a bit. So you definitely want to revise it, definitely taking into consideration any of the comments from the reviewers the prior year. And then with your new project, you want to insert that in there, you know, into the text of the document, and, you know, the code performance, the, you know, the methodology, the justification, all the different sections. Yes, you want to add the new project in, but that's perfectly fine. You know, that can also be done, you know, as a supplement in the middle of a grant period. If you maybe you receive new funding from an agency and you have a project to go and you have a group, you know, of postdocs, graduate students, undergraduates, yourself going to work on this, you can do a supplement to an existing active award for the additional project. But that's going to, again, require a main document. Don't include it in your progress report because it's new and you haven't had progress on it yet, but definitely in the main document. So,
I would like to add that you certainly are going to tackle a different scientific question because you have answered the old question in the previous year. And so based on how big the changes are there, then you have to follow up with the changes in your proposal.
There was a question that Jay and I were handling for Scott about storage. Um, you know, most of the requests we were focusing on computational resources. The storage is something that comes along with that. It definitely is reviewed. It definitely is considered. If you have large amounts of data storage needs, you're definitely going to have to really justify these. By default, all the sites give you 500 gigabytes, and some find that that's sufficient, and many don't. If you're getting into many terabytes, closing in on half a into petabytes, it happens. But some of the sites even limit the storage. SDSC limits storage requests up to 50 terabytes. TAC in Pittsburgh have not done that yet, but that's not to say that we wouldn't do that. So it's something that you're going to have to consider. Your storage definitely justifying it, and also having a plan, not a code performance and scaling for it, but it's something that you're going to have to consider. The question that Scott had asked was long-term storage, and it is something that the sites all have some policy in place, and you want to check each site that you may have an allocation and a storage allocation there. Some will allow them to stick around for multiple months after. Some will assist with continuing them. Some will tell you you've got to move them to some site, your home site or something, and they'll work with you to move them. Or what a lot of our PIs do, they come back year after year. They continue to use the XSEDE sites and renew the proposals, and they're able to keep that storage there for multiple years, if not longer. So
I would like to answer it a little bit, give it a different twist. You can ask for long-term storage, but you cannot ask to park all your data for the rest of your career at some of these at the storage resources. You will be asked to delete data or store it somewhere else from projects that are long gone and that have where the data has been analyzed. You cannot park all the data that you have ever produced and increase your storage quota year after year.
I feel like I've just been reprimanded.
No, I wish, because I would never let an opportunity slip to do that, but no.
Right. I think on scale, I think, if you have a terabyte, that's not really, most sites aren't going to, could be big concern. It's when you start approaching, 50, 100, closer to petabytes, that becomes a big issue. All of our sites have probably dealt with somebody that had a lot of data, and we want to help, we want to be involved, we want to provide the resources, but the long-term parking, as Lars calls it, that's not. You better be prepared. If you think you're going to have a lot of data, you need to have some backup plan for that.
And maybe if somebody wants to unmute and ask a question, I think at this point that is fine too.
Oh, right. Yes. If people have questions, we're definitely happy to chat verbally instead of through texts or chatting.
Hi, Scott here. I've asked a lot of questions in chat. I was wondering if, as you're putting together a proposal, given that it will probably be looked at in future years how you use the resource, is it better to underestimate and risk not being able to complete all of your scientific goals, or overestimate and risk not needing to use all of the resource?
No, you should ask for exactly what you need. If you underestimate, then you get you can't get it done. I mean, there is of course the caveat: if for the whole project it is way too much to ask for a given year, then you kind of suggest to do step one, and then you move on to the follow-up steps. And obviously, you should never pad your numbers and overestimate, because you assume that there will be a cut coming. The moment the reviewer is suspicious of that, it will be noticed. And it will be noticed beyond this one review, because when you come back 3 months later, Ken will assign the same reviewers, or at least partially the same reviewers, to your proposal review, so that this institutional knowledge about a certain group is not lost.
Right. That's exactly correct. We try to keep some consistency with the reviewers, especially on ones that may have been declined, so that they can see that the changes and the updates and revisions are in line with what they were recommending. But even ones that are just renewals year after year, we try to keep that consistency if the reviewers are still on the panel. Again, we always talk about, what we award based on the merit of the proposal. If you can justify it, it's okay to request it. But like Lars said, if you start to pad or game in some sense, the reviewers, they're aware. A large number of our reviewers are also PIs. I'd say 50% or more of them on our peer review board are XSEDE PIs as well. Some of them are some of our largest users on some of the systems. So they have a lot of experience, and they definitely have a good understanding of these systems and have read many proposals. As we talked about, we get a lot of requests. They read a lot of proposals, so they've seen the good ones and they've seen the bad ones, and they've seen the ones that are that they're catching a few things. So
okay, just to follow up, sort of to give some context. I think what I have in mind is that a lot of the time, the science that I'm doing is with like university scale experimental facilities, and they turn around their sort of scientific pace is like on a time scale much faster than a year. So like trying to plan for the simulations that I might need throughout the entire year has been a challenge as I put together these proposals, rather than having sort of like a large experiment that's over several years. If you're trying to support experiments that are
Yeah, so I see that is certainly a problem. And there you have to do your best to kind of anticipate what will come in the next year. It is not ideal, but obviously our process is once a year. That's the typical length or that's the minimum length for a proposal. And yeah, we understand that for some projects that is certainly not ideal. So there you have to do the best you can, explain the situation and do an estimate on fair numbers. Again, present it in the best light for you without crossing the line where the reviewer thinks, oh, that is all nonsensical.
This is Don Krieger. I have an apropos question to follow up with that one. If you apply for a supplement, does that also get seen by the reviewers who reviewed the original application, or is it just seen by the people the stakeholders who own the facilities on which you're running?
Dawn, this is Ken. It depends. If the requests are coming in and they're, hey, I need an extra 100,000 hours to get by this until my renewal kicks in, that we're not going to make that go back to the reviewers. But when they start getting into sizable supplemental requests, and that number of sizable is variable based on the resource. If it's the Bridges 2 and Expanse machine, those are all in core hours. So, 1 million core hours maybe not, it's not super large. But if somebody came in and said, I need 1 million on Stampede 2, that's extremely large, or GPUs or something like that. So depending on the situation, and sometimes we'll take these to the sites. The sites always have reviewers that are very aware of this, the science, the machine, the user base. If they feel uncomfortable, they'll send it back to my staff, and they'll say, let's get the reviewers' opinions in this, because they had some concerns before, and we would like them to be, at least on their radar a little bit and have a voice in this. So it just depends.
I asked this question because of the previous question about having difficulty predicting what's going to come. We also have difficulty predicting what's going to come. And sometimes in the middle of the year, if you get a new batch of data that you need to process that you didn't anticipate, the supplement what you write in the supplement is very much like the original application, or, you know, it's, hey, we used so many hours before, we need that again because we just doubled the data that we're going to be processing.
And then it's certainly better to submit a supplement rather than anticipating in your original proposal, oh, for the data that we have, we need X amount, and because we anticipate there may be more data coming, but may not, and then we ask for 2X. So then it's certainly better to kind of plan for supplemental request halfway through. And there you have to explain why in your specific situation it is difficult to anticipate the workload of a given year.
Great, thanks.
There's another question there from Francisco. The question was, how detailed should a startup allocation proposal be in terms of scaling information? You really don't have to have any scaling information. You just have to have some sense of what you would like to do. You know, the getting the startup is to prepare yourself for the scaling information and for to graduate to the research request. So in the extended abstract, there's not even a mandatory document other than a CV. Just some details about the science that you're going to do. The research that you're planning and or have been funded for if you have funding for it, and then another paragraph or two, some details of, you know, why this particular resource and what you're trying to accomplish with it. Again, startups are, I'll probably say 99% of them are approved in some form. Maybe not 100% if the request is greater than what some of the maximums are, but we definitely try to turn these around so that people can get you know, what do they say? Get your feet wet on the machine and get the testing done and your porting and your benchmarking so that you can graduate to a research request. So,
let me add to that an important point. You ask for a startup to produce the scaling information. Hence, there is no scaling information request required to ask for a startup. And therefore, there's no requirement to have any scaling information in your startup request.
Right. So if you don't have a startup yet, go ahead and submit one. It looks like
and here I specify 4 to 5 paragraphs, but those can be very, very short paragraphs. Each paragraph can be a few sentences. You know, field of science, your work, what you want to do. And what I outline here, what you want to do can be anything. Testing your software, installing your software, doing some scaling studies or developing code. Anything goes, and because anything goes, there are no requirements in that area. Oh yeah, and Julio is commenting, indeed, I'm using the startup to fine tune my parallel IO with the MPI IO. Yes, perfectly good reason to ask for a startup.
some very good questions there. It was, I think,
Diva is asking a question. For instance, I need to run MD simulations for 500 picoseconds on 6 million atoms. Now core wall clock and available wall clock become tricky. Diva, can you unmute and tell us why it becomes tricky?
Yeah, hi, thank you. So like if I want to run my simulations efficiently, you know, and I know that the available wall clock time is say 24 hours. So now the course that I need to choose there, it kind of...
No, that is already you run for 24 hours, you write a restart file, and then you continue your calculation. The wall clock, the time limit in the queue of 24 hours doesn't mean that you have to finish all calculations in 24 hours.
Yeah, that's what I wanted to know, that whether I should like, should I just increase the number of cores and get everything done, or should I use checkpoints and like restart files and just run it?
Absolutely. Because if you just want to get everything done in 24 hours, you will be wasting so many resources.
Yeah,
Well-
that was my concern, and that's why I raised this question. So because so now it's clear to me. Thank you.
You're welcome. Anything else? If not, then thank you all for the attention, and I will move on, and we're going to do some reprimanding with Ken.
you.
Ken, get ready.
Please
Thank you,
be nice to me. Yes, thank you, everyone. Hope you enjoyed. If you have questions, you can always send them to help@xseed.org.
Thank you.
Okay. Look forward to your startups and your research proposals.
Okay, that was great.
Yes, thank you, Dr. Lars, for your help, and Dr. J.
Yeah. Okay, I think I'm going to log off, and we stay in touch and do the usual.
Yes. Take
Sure.
care. Take care, everyone. Be safe. Stay healthy.
Bye.
Bye.